defined on the tangent bundle of our closed manifold, and say that this is quadratic, so it's Tonelli and quadratic at infinity. So what we said is that in this case, the Lagrangian action functional, so this was denoted by SL Q equal integral of L T Q Q prime. This is a nice functional on the space of H1 loops. So this is of class, say, C11 on H1 loops valued in M. Okay, and we proved that it also satisfies the Palais-Mail condition. Okay, so that's good. And also, we also said that it has all critical points with finite Morse index and finite nullity. And so now we would like to do Morse theory, actually to construct the Morse complex for this functional. And so we still have a bit a difficulty because of this C11. So this function is not C2. Actually, the second differential exists, but this is just, say, the second in the sense of Gateau. So it's just a directional derivative, not a Frechet differential. And so there is this small difficulty. And in order to overcome this, well, first of all, since we are interested in doing Morse theory, so we want to have Morse functions, so we want critical points to be non-degenerate. And so let's assume immediately, so assumption. So for every Q in crit SL, this thing which nevertheless exists, this is a non-degenerate quadratic form, meaning that it's associated, the self-adjoint operator which is associated to this is invertible in the strong sense. And this is easily shown to be equivalent to the fact that, so, well, here Q is a one periodic solution of the Euler-Lagrange equation. This is equivalent to saying that the linearized system at Q, so we take the Euler-Lagrange equation and we linearize it along the periodic solution. This equation has no non-trivial one periodic solution. Or if you want, it's equivalent to the fact that the Hamiltonian is non-degenerate in the sense that the fixed point of the first return map are non-degenerate as fixed point of the first return map. All these things are all equivalent. So let's make this assumption, and it's something which is true for a generic Hamiltonian, equivalently for a generic Lagrangian, because we are requiring explicit t-dependence. Otherwise, it would not be true because variations along, critical points would come in S1 parameter families because of invariant with respect to translation. Okay, and then, so once we have this, so in order to overcome this small problem with regularity, what one can prove, I'll state it, is that there exists. So instead of working with the negative gradient vector field, which would be just Lipschitz, one can build a smooth pseudo-gradient vector field. This is the content of the lemma I'm about to write. So there, I call it SL, AX of SL. There exists this, which is a smooth vector field on this Hilbert manifold, H1 Tm, such that, well, several things. Say X of SL is complete. By this I mean integral flow lines exist for all time. Second, SL is a Lyapunov function for this X, SL, meaning that the differential of SL applied to X SL is negative on the complement of the critical set of SL. So on H1 Tm minus critical points SL. And then we also have that this vector field is Morse. Morse just means, for a vector field to be Morse, it means that at every zero, the differential of the vector field, which is well defined at zeros of a vector field, is hyperbolic, meaning that it has no eigenvalues on the imaginary axis. So for every x, no, let's call it q, for every q, which is a singular point of our vector field, meaning this is just the counter image of 0, dxsl q is a hyperbolic operator, meaning that the spectrum of this intersected the imaginary axis is empty. Actually, one can choose this differential to be exactly the Hessian of, so say minus the Hessian, minus d squared SLQ with respect to some Riemannian metric on this manifold. Okay? And so actually all the eigenvalues are actually real. And last property, the pair XSL SL satisfies the Palais-Mail condition. So yesterday I introduced the Palais-Mail condition for a function using a Riemannian metric, but instead if you forget about Riemannian metrics, you just have a vector field and a functional. You also have a notion of Palais-Mail sequences, which is just, so a Palais-Mail sequence in this setting is a sequence, say QH, such that, well, SL of QH converges to something, and the differential of SL QH applied to the vector field X SL at QH goes to 0. Okay? When your vector field is precisely the gradient, you find again the standard Palais-Mail condition. These are Palais-Mail sequences in the standard sense using a metric. But this is a sort of, say, metric independent definition of Palais-Mail sequence, and this is what is needed. Okay, so one can prove that one has this nice thing, and this is not difficult. One has just to, so the gradient would be already fine, except from the fact that it's not smooth. And so what you have to do is actually to build this pseudo-gradient vector field close to critical points. And because when you are outside from critical points, it's very easy. You just consider constant vector fields in some neighborhood, and then you patch everything with partitions of unity. So it's not a difficult thing to prove. Okay, so one has this lemma. And so this is good news because these are exactly the conditions which allow to have a well-defined Morse complex. So let me say something now in general about, say, the Morse complex for functionals on infinite dimensional manifolds. Just to have a clear statement of a setting when the Morse complex, the one we know from finite dimension, extends without any difficulty to infinite dimension. It's not the most general setting one can think of, but it's what we need. So the setting is, so we have this M, which is a Hilbert manifold. So I want to state everything in the, and well, without using Riemannian metrics, to try to be a bit more natural. So we have a Hilbert manifold, M, and then we have X, which is a vector field on M. And let me state now the assumptions we need. So maybe I'll state them all here, and those which are not self-evident, I will define them the other blackboard. Okay, say X is smooth. Well, actually, C1 would be enough, but let's not be picky on regularity, because we saw that actually regularity of the vector field is not something which is difficult to obtain. The second is that X is Morse, exactly in the sense I said before. And critical points, and so singular points, have finite Morse index. Okay, so maybe here we need a bit of explanation. So we have this singular point X. Now we said that so the differential of X at this singular point has no purely imaginary spectrum. So Txm splits. If we do the spectral decomposition, we have the spectral decomposition EXU, EXS. This is the part corresponding to the positive part of the spectrum. And this is the part corresponding to the negative part of the spectrum. I'm always referring to the spectrum of dxx. And this is called the unstable space. This is called the stable space. And what we want is that the dimension of EUX, we want this to be finite. And this is by definition the Morse index of the singular point X. Yep. No. It's enough to this condition, that hyperbolicity. You don't want to have eigenvalues on the purely imaginary axis. Then, positive means, sorry, positive real part and negative real part. Okay? Okay. Then, third, so let me say, or let me derive all consequences of this. Then, so actually, these are, I mean, the fact that the spectrum, the fact that the operator is, the singular point is hyperbolic are exactly the assumptions that you need to prove the stable and unstable manifold theorem. So this fact implies that the unstable manifold of X, that is the set of points in M which flow towards X for S going to negative infinity. This space here, this is an injectively immersed smooth manifold with tangent space at X equal to EU X. And the same is true for the stable manifold, where the definition is the same, but S goes to positive infinity. And here you get that the tangent space is the stable space, EXS. Okay? So in our setting, this unstable manifold will be finite dimensional because the index is finite. And instead, the stable manifold will always be infinite dimensional, but with finite codimension. And they are nicely, for now, smoothly immersed submanifolds. Okay. Then condition 3 is that X admits a C1 Lyapunov function. Let's call it F, which, as I said, just means that df applied to X is less than 0, strictly less than 0, on M minus the set of singular points of X. And now the existence of this Lyapunov function, so condition 3, now implies that these stable and unstable manifolds are not only injectively immersed, but they are actually embedded. So the unstable and the stable manifolds are embedded. Okay? This is also something quite standard in, say, hyperbolic dynamics. Then for the pair XF satisfies the Palais-Mail condition, exactly in the sense I wrote before. Now, Palais-Mail conditions are defined only in terms of the vector field and the function. There's no metric. And 5, X is forward complete. So the flow of X exists for all. So since X is smooth, we know that the Cauchy problem is well posed. So Cauchy problem on infinite dimensional, say, Hilbert manifolds or even Banach manifold is not, when your vector field is at least Lipschitz, it's not more difficult than in Rn. ODEs are the Cauchy-Lipschitz theorem for existence and regularity of solutions of Cauchy problems of ODEs is proved in the same way in Rn as it's proved on a Banach space. There are no difference, so the Cauchy problem is well posed, and we actually require to have existence for all time, say positive time. And the last assumption is that X is Morse-Mail. That is, that stable and unstable manifolds always meet transversally of two different critical points, say for every X and Y singular points of X. They meet transversally. Okay? And this, instead, this Morse-Mail assumption is something that you, once you have all the other conditions, you can always achieve this by a small perturbation, by an argument which is much easier than in Floer homology, of course. Here you have really a lot of freedom to perturb. Okay, so these are the assumptions. Let me see, I have to make some comments about, maybe the only comment is this one, that these assumptions here, Palais-Mail and completeness of the flow, these are somehow antagonist assumptions, meaning the following, that they sort of work in different directions. Because if you have a vector field X, so of course the dynamics of X up to time parameterization does not change if I take X and I multiply it by, say, a positive function. The dynamic will be the same. So if I multiply X by a positive function, which at infinity goes to 0, I can make it forward complete, because I can slow it. Maybe there are solutions which do not exist for all time. They blow up in finite time, but if I make the vector field sufficiently slow, I can achieve forward completeness. But then I will increase the number of Palais-Mail sequences, because if X is smaller, it's easier to have this condition that ds applied to X goes to 0. And conversely, if I want to achieve Palais-Mail, it's easy. I can achieve Palais-Mail if I multiply by a function which grows at infinity. But then I will lose my completeness. So it's a sort of a balance between two things. Okay. So this is the setting for which the Morse complex is defined. So let me briefly then recall the construction. So that we see also where the assumptions are used. And so the key fact first fact that one should prove is that unstable manifolds, sorry, I didn't write an important assumption. F, there is this Lyapunov function F, and this F is bounded from below. Okay? You can work and do something more generally, but we actually, our function is the Lagrangian action function, and it is bounded from below. Okay, and the key fact is that the closure of all unstable manifolds, this is a compact set for every X singular point for X. And this you can prove it by starting from the observation. Well, you have to use basically almost all the assumptions. So locally, near the critical points, this is a finite dimensional manifold. So locally, it's a nice compact disk. And then you have to use the fact that the flow is complete, and the Palais-Mail assumption, and the fact that the Lyapunov function is bounded from below, to guarantee that this small disk, then when it evolves through the flow, does not go to infinity, and it actually remains, its closure is compact. And it's a nice thing to try to prove. You have to do, actually, technically, you have to do a bit of a induction on the number of critical points that you have below level X. And then you can prove this thing. Okay, so this is the key fact. And let's see what we can do then. Then, once we have this, we can do the following. So given a natural number k, we construct this set here. I'll call it mk. Mk, this is the union of, I take the phi will be the flow of X. Maybe I'll write down X here to remember. I take the forward evolution, I take here R plus of Ux, where Ux is a neighborhood, open neighborhood of X. And this, this union is made on all singular points of Morse index less or equal than k. Okay? You take small balls around all critical points with Morse index at most k, and you let it then flow down with the vector field for positive time. And then the thing one needs to prove, this is a lemma, is that if the UXs are small enough, if these are small enough, then it's very easy to, so the relative homology mk modulus mk minus 1 is very easy. So the Hj, the relative homology group of mk modulus mk minus 1 is, well, it's 0 if j is not k. And otherwise, when j is k, this is precisely, I'll call it mkx. This is the free abelian group generated by singular points of index exactly k. Okay? A bit like in finite dimensional Morse theory. So let me make the usual picture which somehow proves this. We'll take the assumptions on the vector field. So this lemma is actually, this follows from the Morse-Mail property, I would say. So let me do the usual picture of a, instead of course, it's a bit difficult to draw some infinite dimensional manifold, so let me draw a finite dimensional manifold. I don't know, something like this. So this is a sphere S2 embedded in R3 in this way, and this is the height function. And so here, critical point of index 0 are here. So the set M0 is just, well, just neighborhood of critical points of index 0. If we let them evolve, nothing basically happens. So it's something like this. This is M0. M1 is instead, so critical points of index 1, I have one here and one here. And if I let evolve a small neighborhood here, it will do something like this, and also on the other side. And this will do, I don't know, something like this, and then something like this. So M1 is so the same picture, but then I also have like a handle here and another handle here. And M2 is now the whole thing, the whole duck. Okay? And so, yeah, from this picture, it's easy to see that when you pass from mk minus 1 to mk, what you do is you're attaching k-dimensional cells, and that's why you have this, this thing, the usual thing of Morse theory. So the thing is that H star of this mk minus 1, this is a H star, so using excision is the same as H star of the union of, say, local unstable manifolds modulo their boundary of local unstable manifolds, where these are critical points of index exactly k. Okay? Okay, so one has this, and then one has the usual fact. Then, so then we have this sequence of sets, M0 containing M1, etc., containing MK, containing the, say, the bigger one, let's call it M infinity. This is just a union of all of them. And this is, so saying that the relative homology vanishes when the index J is not K is exactly saying that this is a cellular filtration. What in topology is called a cellular filtration. And cellular filtrations are the usual methods to compute homology. So there's a general procedure. Whenever you have a cellular filtration, you can compute the homology of their union, in our case M infinity, just by this procedure. We consider, so let's write it here. We consider the only space H which is allowed to be non-zero, so HK of, well, maybe I'll write it here so I have more space. So how to recover the homology of M infinity out of this data? So we start with our MKX. As I said, so one wants to build a homomorphism, which is actually a boundary from MKX to MK minus 1x. And this is defined like this. So MKX, by definition, this is just HK of MK minus 1. Okay? And then this, with the usual boundary operator, goes into HK minus 1 of MK minus 1, using the boundary operator in singular homology of pairs. And this, by the inclusion, goes into HK minus 1, MK minus 1, MK minus 2, which is this one. Okay? And using the fact standard properties of the boundary operator in singular homology, one gets, so this is a standard theorem, one gets, of course, that this is a complex, d square equals 0. This is trivial. And instead, what is non-trivial but true, and that's why cellular filtration are useful, is that the homology of this complex here, so M star x with this boundary operator, is isomorphic to the singular homology of our set M infinity, the union of everything. Okay? So this is the Morse complex. And then here what we have is also, let me write it here, or maybe let's write it here, the singular homology of M infinity. This is also isomorphic to the singular homology of the whole M, because this is actually a deformation retract. So we're in a non-compact setting. This is a proper subset of this. However, this retracts on this just by using the gradient flow, because if you take a point here, you use the gradient flow, eventually it will have to enter here. So it's quite easy. Okay, so this is the Morse complex. And of course, so say theorem 1, of course, theorem 2, the other nice thing is that this boundary operator, which is defined, say, using singular homology, instead you can actually compute it using intersection theory. So we said that these spaces here are free abelian groups generated by singular points, and there is the formula that also Mihai wrote. So the boundary of X is the sum of some coefficients n x y y, where this is a sum over all singular points of index 1 less, index of y, index x minus 1. And let me briefly recall the definition of these numbers, nxy. Well, here in this identification, when I identify this, yes? Exactly. I mean, the fact that every Hilbert manifold admits a Morse function can be used to show that every Hilbert manifold is then a CW complex. But then, yeah, then you have to show that every Hilbert manifold admits actually a Morse function which satisfies the Valles-Mail property, which is not, I mean, it's true, but it's not completely trivial. Because, yeah, you have this Valles-Mail property to somehow ensure. But it's true. Yeah. Okay, now here I was just saying this identification that this relative homology is this free abelian group. So in this identification, actually the identification is done by, you have to choose generators of these local, you have to choose a generator of the relative homology, a local unstable manifold modulo its boundary, which means it's equivalent to choose an orientation of the unstable manifolds. So what you do to define these nxy are these steps. You fix arbitrary orientations of unstable manifolds, all of them. Then each, because they are finite dimensional, so that's fine. So each stable manifold now is co-oriented. So these stable manifolds are instead infinite dimensional, but they are finite co-dimensional, so they have a finite dimensional normal bundle, and this is oriented by, because at x their normal bundle is identified with the tangent space of this. And then when you have an oriented manifold and a co-oriented one, and you intersect them, then you get that the intersection is oriented. Well, it's a manifold because of Morse-Mail, but it's also oriented. And then you obtain that in the particular case when the difference of Morse indices is 1, then this intersection, this is a finite union of lines. And each of them, and so nxy is obtained by, is the sum of, so for every of this line you add, so add +1 for every line on which, say, the vector field x is orientation preserving. So the vector field x always goes down. But of course, instead the orientation given by this recipe may be something else. Some of these are oriented down, some are oriented up, and you add 1 whenever it's orientation preserving, and you add -1 otherwise. Okay? And then one can think a bit, and by looking what this operator really does, it really does this one. Okay. So this was a quick review of Morse homology in this infinite dimensional setting, which is so simple that everything goes like in the finite dimensional setting. Okay, so this is our, and so because of this, we now have a Morse complex for the Lagrangian action function. Now, the other side of the story is the Floer complex, and this is what Mihai is constructing. So here I'll be really very sketchy. I'll just basically fix the notation I will use and just say the couple of differences that we have since we are working now on cotangent bundles which are non-compact. Okay? And so what is the starting idea of the Floer complex? In some sense, it's one of the oldest ideas in mathematics. You take a theorem and you transform it into a definition. So there is this theorem here which says that in Morse theory, this boundary operator coming from topology is described in terms of intersection numbers. In Floer theory, there is no topology you can use, but you actually define the boundary operator using this formula. So you use a theorem and you transform it into a definition, and then one gets some very interesting thing. Okay, so let me now go to the Morse complex. Sorry, Floer complex. Floer. So now we have the objects are instead we have a Hamiltonian, smooth, time-dependent, defined on the cotangent bundle of M, and say all one periodic orbits are non-degenerate. Assumption, and X should be also, say, for instance, quadratic at infinity. So again, its behavior on a compact set doesn't matter, but at infinity it should have some quadratic growth analogous to the one I wrote for L. But actually here no convexity instead is needed. H is quadratic at infinity, and so we know, well, we have this Hamiltonian action function AH, and this is a Lyapunov function well, not for a vector field which generates a flow, but for the Floer equation, the one that Mihai wrote for, so the equation is dsu plus j, this almost complex structure, which might even depend on time. So I write GTU times DTU minus XH. This also depends on time, U equals 0. So these U's are maps from R cross T into T star M. Here the variable is S. The name of the variable here is T. And this is the Floer equation. So again, this is a PDE. It does not define a flow. I cannot prescribe U at time 0 and then hope to solve this equation for all time. I cannot hope for existence of, I could hope for uniqueness, but for existence, I cannot hope for that. But the idea is exactly not to consider it as a flow, but instead to consider it as a boundary value problem, well, asymptotic boundary value problem. One looks for solutions of this which connect stationary solutions, so solutions which do not depend on S. And so solutions which do not depend on S are actually solutions, so are periodic orbits of the Hamiltonian vector field. Okay, and AH decreases on these solutions. And so the thing was, so let me give name to things. M, let's call it M boundary. M boundary XY. This is so the moduli space which are considered to build the boundary. So these are the U's, which are solutions of the Floer equation, and such that U at minus infinity is X, and U at positive infinity is Y. So these are these cylinders which connect X and Y. And then, so for generic, well, write this for generic H and J, but one can actually fix H and choose a generic J, or fix J and choose a generic J, whatever. One gets that these are actually manifolds of dimension, the Conley-Center index of X minus the Conley-Center index of Y, which I want to define. And the only observation is that, so remark, is just that when H is Legendre dual or Fenchel dual to L, then, and say X is, as usual, I write it as QP, then this Conley-Center index of X coincide with the Morse index of Q. So the Conley-Center index defined using symplectic structure on the cotangent bundle coincides with the Morse index of Q as a critical point of the Lagrangian action functional. This is the important thing. And then the other thing is that these MXY, as Mihai explained today, these are compact in this infinitely lock topology. And here, well, the analysis is basically what Mihai explained today. So the only difference is that, well, here we are on a non-compact manifold. He also dealt with non-compact manifold, but when he had Lagrangian boundary conditions. Instead, here we have it's periodic Floer homology, it's cylinders. So the first thing one has to show is that all these cylinders, that these cylinders are containing a compact subset of our cotangent bundle. And this in general, it would not be true. It's true under various combinational assumptions on the Hamiltonian and on J. For instance, this is true if H is asymptotically quadratic and, yes? Yes, so say pre-compact. Pre-compact is infinitely little. The limit is not anymore in this space. Yes. So, yeah, what people would say is compact up to breaking, and probably next time you'll spend this. I didn't want to say today because, yeah, pre-compact. Yes, exactly. Yes, because a sequence of cylinders like this could converge to something which is not anymore in the same space. Here there is X, here there is Y, and here there is Z. And you have this sequence of cylinders. In the limit, you find something in a different space. Okay. So I was saying that, so if H is quadratic at infinity and J is sufficiently close to the Levi-Civita almost complex structure, the one which is used, for instance, induced by a metric on M, then one has this compactness. Or also if H is one of the Hamiltonians that Alex was talking about yesterday, so radial, depending radially on this with respect to a Liouville vector field, which we have on cotangent bundle. So, and if J is adapted to this Liouville structure. So there are big classes of Hamiltonians and J's for which this is true, and we can use this. And then, of course, then the Fk of H. So I will not put the C. I always, so for me, the Morse complex, I just use M, and the Floer complex, I just use F. And of course, then the consequence will be that Morse homology will be HM, and Floer homology will be HF instead than FH. But it doesn't matter. Okay, so this is the free abelian group. Well, now I don't want to talk about the orientations in Floer homology, so let me say the Z2 vector space generated by periodic orbits with Conley-Zender index equal k, and then the boundary from fkh to fk minus 1h. So this now does not have a definition in terms of topology, it just has a definition in terms of intersection number, and it's the, so x goes into sum over all y's of the number, say modulo 2 of mxy, say modulo the action of r times y, where these are solution of Conley-Zender index 1 less. Okay, so this is the, and the non-trivial things are that this is a boundary operator, so this square is 0, and that the homology, so to be precise, this complex so if you change the almost complex structure J, you get isomorphic chain complex. So changing J, get isomorphic complexes. And if instead, if you change also the Hamiltonian, you get homotopy equivalent. Complexes. So in both cases, at the level of homology, you get isomorphism. So the Floer homology is the homology of this complex here. Does not depend on H and J in these classes. Okay. And yeah, and what we want to do is to compute this Floer homology in the case of cotangent bundle. And so let me now state precisely the theorem that I want to prove. So this form of the theorem is due to myself and Matthias Schwarz. And say the first part of the theorem is, I don't know, 2006. The first part is published, and the second part of what I will write instead is nowhere written. So, 2012, but somewhere we will write it down. So it says just that if L is or maybe if H is Fenchel dual, so if H is Fenchel dual to Tonelli and quadratic at infinity Lagrangian, L, then there are, say, explicit, and I will clarify what this explicit means. There are explicit chain complex isomorphisms so one is, let's call it phi. It goes from the Morse complex of this pseudo-gradient vector field, which is associated to the Lagrangian action function, to the Floer complex of H. And the other one I'll call it psi, goes the other way around. F star H into M star XSL. And this isomorphism preserves, which preserve for instance, the action filtrations. So here, critical points come with an action, and the boundary preserves sublevels, because the boundary operator always maps a generator X into something with lower action. And these isomorphisms, so both are filtered. The filtration on critical point coincide, because we already said that on solutions, the value of the Hamiltonian and the Lagrangian action are the same, and these isomorphisms preserve these action filtrations. And of course, they also preserve and the splittings into, say, free homotopy classes of loops. Well, of course, another easy thing is that in the boundary of X, you will find only loops which are freely homotopic to X, because there must be a cylinder. So this is almost trivial. But what I say by explicit, so here the thing is that these things are explicit, meaning that there is, so we can describe both these isomorphisms, saying that these are again defined by a counting procedure. So there is some moduli space of maps, and you count them and you obtain these two maps. This is what I mean by explicit. And so then a corollary of this fact, and this is a theorem which was previously also proved by Viterbo, I think 1996, and by Salomon and Weber, also 2006 it's published, but they did it before us. And so the consequence is that the symplectic homology of the cotangent bundle of M, or maybe the cotangent this bundle of M, is isomorphic to the singular homology of the Fleet loop space of M. So again, using Z2 coefficients. And of course, this follows from this just because the homology of our Morse complex is the homology of the underlying manifold, and the underlying manifold is this space of H1 loops, but this has the same, this is homotopical equivalent to the space of smooth loops, and so this is the homology one gets. Okay? And so this is a proof which compares these two complexes, so it's heavily based on the Legendre transform. The proof of Viterbo is instead, probably of these three proofs, the proof of Viterbo is the one which requires less, I mean, analytically, it's probably the one which is technically simpler. It's based on generating functions of finite dimensional constructions, but the idea is probably more involved. It's a bit less direct. There are more limits involved. And the proof by Dietmar Salomon and Joa Weber is probably the nicer from the point of view of the geometric content, because it shows that this Floer complex in a certain limit degenerates and becomes a Morse complex associated to a heat flow, so some parabolic equation which are associated, under which loops on a manifold evolve. But there the analytical complexity is quite heavy, and our proof is probably a bit in the middle in terms of complexity. Okay, so in the last half an hour, I don't want to prove this theorem, which I will do maybe tomorrow, but rather try to explain, try to motivate the definition of phi m psi. This is what I would like to do. So we will see that phi and psi are defined counting something, counting some solution of some problem. And I would like to use some of the observations I made yesterday to motivate these, the definition of that we will do. Actually, so the existence of phi, this is the one which is contained in this published paper from 2006. And instead, the existence of psi is the one which instead is not written yet. But so maybe tomorrow I'll prove you instead of the existence of phi, because you can read about this, I will prove the existence of psi, so at least it's written on the blackboard. Okay, so remember, so here we have these two. What is the problem? We have these two complexes. In some sense, there is a one-to-one correspondence between generators, because H is the Fenchel dual to L, so there is a correspondence between periodic orbits. But the problem is that the two boundaries are defined in completely different ways. Here we are on the cotangent bundle, and we use this Floer equation. And here we are on the loop space of M, and we use this pseudo-gradient vector field. And there's a priori no reason. In fact, this is not the identity. These phi and psi, they are not identity. The identity would not be chain maps. That's the problem. And so what? But the thing we saw yesterday was that there was this diffeomorphism from the loop space of Tm to the loop space of T star M, which had this, this was such that if we read the Hamiltonian action function on, which is defined here, if we read it here on the loop space of the tangent bundle of M, so we apply to QV, then what we get is S, the Lagrangian action of Q, minus this function U QV, which was a function just going, which was 0 on the 0 section, and then growing on the fibers. This was the thing. So the first observation is that because of this equality, it is actually very easy to build a pseudo-gradient vector field here. So the first thing is, so first fact, build a pseudo-gradient vector field for AH composed theta on lambda Tm, and this pseudo-gradient vector field, let's call us X AH composed theta. I write also always the function here so that I remember who the function to whom the vector field refers to, with the following properties. So, because the function is like this, so I can make the 0 section to be invariant. So the 0 section, this 0 section of lambda Tm, which is actually isomorphic to lambda M, is invariant for the flow. So this vector field is tangent to the 0 section, and actually this vector field restricted to the 0 section, to this 0 section, lambda Tm, is actually XSL. So on the base, we can just consider the vector field, the pseudo-gradient vector field of the Lagrangian action function. And on the fibers, we just go to infinity. So the other assumption is just that the projection, so the flow of this vector field, A composed H, A composed theta, commutes with the projection pi from lambda Tm to lambda m. So here there will be many projections involved, from lambda Tm to lambda m, lambda T star m to lambda m. I will always denote them by pi. There should be no danger of confusion. And since the function is going down outside from the fibers, the behavior will just be that orbits outside the zero section tend to the zero section for s going to negative infinity, and instead tend to infinity, so they flow away along the fibers for s going to positive infinity. Okay? This is just because it's an easy functional. It's a nice function on the zero section plus something which goes down. So we have this. And because of that, even if, so this is a function defined on an infinite dimensional manifold, and now critical points have infinite Morse index. But now it's, so let me write down who are the stable and unstable manifold with respect to this flow. The unstable manifold, so critical points are always of the form Q0. They are on the zero section. So with respect to this XA composed to theta, I will write A, I will not always AH, because the Hamiltonian is fixed. This unstable manifold, this is just the unstable manifold of Q with respect to XS pi minus 1. So we take the finite dimensional unstable manifold on the zero section, and then we consider the whole fiber on that. Okay? Just because the function goes down on the fibers. And instead, the stable manifolds of XA composed theta, this is just the stable manifold of Q XS. Okay? So this was already infinite dimensional and it remains infinite dimensional. It's contained in the zero section. This instead was finite dimensional, but because of this pi minus 1 becomes infinite dimensional. And now the Morse complex of this vector field XA composed theta is really equal to the Morse complex of just SL. Well, just because of the Morse complex, meaning defined by using intersection stable and unstable manifolds. Just because stable and unstable manifold can intersect only on the zero section, where it's, and the restriction there of the vector field is precisely, sorry, was XSL. XS is precisely this vector field here. Okay? So this is the first thing. Second thing, now, so we understand completely this vector field. So now let's use theta, so, and this was a vector field here. Let's use theta to push this vector field on this other side. So let's define x just of AH to be the push forward by theta of x AH composed theta. So we take the vector field that we had here and we push it there. So by construction, this is a pseudo-gradient vector field for the original action function AH. Okay? It's defined here. It's defined on lambda T star m. And it's a pseudo-gradient vector field for that. What can we say about now stable and unstable manifold? So if now we have, what is the unstable manifold of a critical point x now with respect to this XAH. Well, this is exactly the same system we had here, just that we pushed everything here. So this is precisely theta of the unstable manifold of theta minus 1 x with respect to the other vector field, XA composed theta. And so, what is this? Maybe I should write somewhere the definition of theta. Well, no, not for. So recall that theta, I'll write it here, theta of QV was Q dVL PQV plus Q dot. This was the definition of this diffeomorphism theta. Well, this is the unstable manifold of this, and this theta is fiber preserving. So this remains the same thing. This is actually pi minus 1 of the unstable manifold of, say, the projection of x with respect to XSL. This is the unstable manifold. What about the stable manifold of XH? This is also easy to compute. Well, it's again the same thing. It's theta of the stable manifold of theta minus 1x with respect to the old vector field, A composed theta. This is, we wrote it here. It's just this stable manifold, and this was contained in the zero section. So what do we find when we apply theta to something which is contained in the zero section? That's theta. So now V is 0 because we are in the zero section. So this V will not appear. So what do we find? We find the set of QPs in lambda T star M such that Q is in the stable manifold of the projection of X with respect to the Lagrangian pseudo-gradient vector field, XSL. This is Q. And instead, P is dVL TQ Q dot. So P is dVL TQ Q dot, because V is 0, was 0 on that side. Or equivalently, Legendre duality, this is equivalent to saying that Q dot equals dPH TQP. Legendre duality. Okay? So these are our unstable manifold and our stable manifold. So now we have this situation. On the loop space of our cotangent bundle of M, so on the loop space of T star M, we have two things. We have a pseudo gradient, so we have this XH, which is a pseudo gradient vector field for the Hamiltonian action functional, and which has nicely defined unstable and unstable manifolds, which are written here. The second thing that we have instead is we have this Floer equation. The Floer equation is like a it's like a gradient flow equation, but which defines no flow. We have like this, say, gradient equation, this Floer equation. So dsu plus gtu dtu minus the vector field xh tu equals 0, which again is it's again I mean, it does not define a flow, but it's still a gradient equation for the same function. It's defined on the same set, loop space of T star n, and again for the same function. Okay, now what is the recipe? So what would you use? So in Morse homology, when you have on the same manifold, you have one function and you have two different, say, pseudo-gradient vector field. And you want to show that in this case, the two Morse complexes are isomorphic. Then it's very easy. So this is a side. I think we just need to keep this. This can be raised without any danger. So again, an abstract thing about Morse homology. Say that on M, we have X and Y, which are pseudo-gradient vector fields for the same F. Okay? And you would like to build an isomorphism from the Morse homology of X to the Morse homology of Y. So critical points are the same, it's just that the flow lines are different. What do you do? Well, you do the obvious thing. You define it by counting, and what do you count? You count intersection between unstable manifolds with respect to this dynamic, the dynamics of X, and stable manifolds with respect to the dynamics of Y. So you would build something, an isomorphism, let's call it phi, which goes, so X, a singular point, well, this is just a critical point of F. This is mapped into sum, and then you count the intersection between unstable manifold of X with respect to vector field X intersected stable manifold of Y, but with respect to the vector field Y. You count, say, maybe modulo 2. If you don't want to use orientation, you write Y, and this is a sum and the Morse index of Y equals the Morse index of X. Why is this an isomorphism? That's also very easy because, well, here it will be of this form. So X will be such an intersection because X is both in the unstable manifold of X and in the stable, I mean, it's in the stable manifold with respect to both flows because it's a common critical point. And then there is a sum of something else, some coefficients nxy, y, but where here the crucial thing is that fy is less than fx. So this means that in terms of the generators, of the natural order on the generators which is induced by the function, this operator has it's triangular. One's on the diagonal and then something strictly triangular. And these things are always isomorphisms. Okay? So this is an isomorphism already at the level of okay, so this is what you would do in Morse homology when you have two different functional. One functional but two different gradient vector field. Now the situation is that we have one gradient vector field, which is fine. The other one instead is the Floer equation. The Floer equation, as I said, does not define a flow, but in a certain sense, one can still talk about what are the stable and unstable manifolds, say, a la Floer. One could interpret stable and unstable manifolds a la Floer as these sets. Let me write it here.
So the unstable manifold, let's say the Floer unstable manifold. This is not a serious definition, it's somehow heuristics, but let's define it like this. The Floer unstable manifold of X, I want it to be, well, this should be like flow lines flowing off from the critical point, from the periodic orbit X. So these are maps from U, not defined on the whole cylinder, but on the half cylinder, so R minus cross T into T star M, such that U solves the Floer equation, and U at minus infinity is X. So half cylinders which flow off from X, and no other assumption. So in some sense, this is, I'm not putting any boundary condition on 0 cross T. So this is an undetermined problem. In fact, this, one expects this to have, this space of solution should be somehow infinite dimensional. Although it's not really clear whether this is really an infinite dimensional manifold. But we will not care about this. But in some sense, this is what should be considered as the unstable Floer unstable manifold. And similarly, we have the Floer stable manifold, where we have exactly the same thing. Sorry, but these are defined on cylinders of the form R plus. So right cylinder with values in M. And this time, U of positive infinity is X. Okay. And now let's follow the recipe. So the recipe is that we want to define, first of all, an isomorphism phi from the Morse complex of X SL to the Floer complex of H. Then we choose a generator here, so Q. We choose a generator here, let's call it X. And we would like, again, to define these as counting some moduli spaces. And what is the relevant space of maps? So let's call it M phi of QX. So we should intersect the unstable, so here's the point. So this thing, I wrote this, but this is canonically equivalent to M star of X A, okay? So that now we have, because those were our two main objects, XA and instead this gradient flow equation. So I should consider on one hand the unstable manifold of the critical point here, which is exactly this object here. And I should intersect it with the stable manifold a la Floer, which means, well, these are defined as subsets in the loop space, and these instead are a space of maps. But morally, what this means is that I should consider space of maps here, such that at 0, they belong to this object. So what I should consider are U's, which are defined on stable manifold a la Floer. So R plus cross T into T star M with the property that U solves the Floer equation. U at positive infinity is X. So here I wrote that I'm in the stable manifold of X. And then I should add that actually I'm in the unstable manifold here, which means that the projection, if I look at this expression, the projection at U at 0 dot, should belong to the unstable manifold of Q with respect to the pseudo-gradient vector field SL. Okay? So this recipe suggests this as a definition of moduli spaces. And if one looks at this definition, this does not look that bad, because this is a Cauchy-Riemann equation which is defined on a Riemann surface with boundary. And on the boundary, so the asymptotic is fine, and on the boundary, we require U to project onto some finite dimensional manifold. If this was just a point, if we project just to one point, we would be saying that U should be above some curve in M, and this is a boundary condition of Lagrangian type, because fibers, inverse image of pi, are Lagrangian in T star M. And Lagrangian boundary conditions agree very well with the Cauchy-Riemann equation. So this looks like a well-posed, and then we just consider a family of such problems with more parameters, because this is a finite dimensional manifold. So this has very good possibility of defining a finite dimensional space. And this is actually what works. This is the moduli space using the definition of phi. Let me just conclude instead writing what is instead M psi. And this is actually what we understood by using these heuristics. We wouldn't have guessed that this was the right definition before. So now we want to go from Floer homology to Morse homology of XS. And we do the same thing. Now we have, again, this is we identified with the Morse homology of XA. Here we have X this time, and here we have Q. And now we want to define M psi X Q. So again, this time we have to intersect stable manifold on that side with unstable manifold on these sides. So this should be U's, which are now defined on R minus cross T with values in T star M. Again, U should solve the Floer equation. U at negative infinity should be X. And now what is the condition? The condition is that if I can read it from here. I want U at time 0. So let's write that U0 dot, let's call this Q naught P naught. I would like this to satisfy this equation. So Q naught should be in this finite codimensional manifold, Vs Q with respect to X SL, and P naught should satisfy, for instance, this equation here. Q naught prime equal dph T Q naught P naught. Okay? So if you believe in these heuristics, you guess that this should be the right moduli space of functions to look at. And at first sight, this looks a bit weird. These are not, this boundary, so this is perfectly reasonable, but this boundary condition is not of a Lagrangian. Here we are imposing that Q is in this finite codimensional space, and this we have this funny condition. But actually, this is not a funny condition. It turns out to be a condition of, say, Hardy type, and tomorrow I'll show you that this is actually a very well-posed and nice problem, and this defines the right isomorphism going from here to here. Okay, I'll stop here.